everyone, and welcome back. Today we're going to be continuing our journey through real analysis and investigate a very important question. Since real analysis is going to be pretty much the foundation of your typical mathematical foundations in single variable calculus, we need to make sure that we're choosing the right foundation to build upon. In the last video, we talked about mathematical induction, which is a common mathematical principle that is used to prove several different relations and inequalities and divisibility properties and so on like that. And one of the things that we used to prove mathematical induction was something called the well ordering principle, which I'm just going to abbreviate by WOP for short. And I asked the question there, the well ordering principle is fine, and in short it says that every non-empty subset of the natural numbers has a least element. Is it really the most foundational thing that we can assume without having to go too far down into, say, Zermelo-Fraenkel set theory? And of course the answer is no, else I wouldn't be having this discussion. So what I want to do is introduce two other things that you can actually build your single variable calculus and several other things from that are not the well ordering principle. And in addition, I'm going to show that all of them are equivalent to each other in terms of their assumptions, right? So let's formally state the question that we're going to be answering. So we take this as axiomatic, right? So we take this well ordering principle as our foundational axiom, right? And of course, obviously, no, there's going to be two other ones. There's going to be one, or I guess you could call it two since the well ordering principle is the first. The second is called the axiom of choice. And the third is called Zorn's lemma. And one can show that if you take any one of these three as your axiom, then you can prove the other two, regardless of the one of the three that you have chosen. Obviously, by the names of these three, well ordering principle, Zorn's lemma, and the axiom of choice, you probably can take a guess of what a lot of people usually take as their axiom from the three, and in particular that would be the axiom of choice, which is built inside of their Zermelo-Fraenkel set theory foundations, right? So now that you know what we're about to dive into, let's dive right in. So let's introduce the first definition that we need in order to discuss the axiom of choice. So we're going to define omega to be a non-empty set of non-empty sets. So in some sense, it's a set of sets that has at least one set in it, and each of those sets within that bigger set has at least one element in them too, right? So it's a set of non-empty sets. So then we define a choice function, f, on that collection of sets, and it's a function obviously from the set of sets into, in here, when we say the union of S. So you take all of those sets inside of omega and you unionize all of their elements together. So that's obviously the codomain. So that's obviously the codomain of our choice function f, with the additional property such that for any set you choose within that collection, this choice function takes an element in that set and returns it, right? So that's what we mean by f of s as an element of s, right? So I give you a set within this collection, and you give me back an element within that set for which I have chosen. So if we were to do a little Venn diagram of this, right? So let's assume that this is our omega set. So this omega set has a bunch of sets in it. For example, we can call this, for example, set 1. We can call this, for example, set 2. There's possibly many other sets in this set. And for example, this set S1 has like x1, x2, and several others. And this set S2 has elements like y1, y2, and several others. They could all be singleton sets. That's not required here, of course. And this function, or what we call a choice function, takes it and returns a particular element. So for example, this set is mapped to some element, for example, xk. This set is mapped to some element, for example, yk. and this is going to continue onwards, right? So omega is just a set of sets, and this choice function takes a set as its input and returns an element within that set of its input and returns it in the range. Okay? So that's what a choice function is. So, big question. Does there always exist a choice function f on that non-empty collection of non-empty sets, right? So this might not be obvious at all, but this is where the axiom of choice comes in, right? So it says the following. So some people call it Zermelo's axiom of choice. Zermelo's axiom of choice, which I'm just going to abbreviate as AOC. So the axiom of choice says the following. So if omega is a non-empty set of non-empty sets, so a non-empty set of non-empty sets, then there always exists a choice function on this collection omega, right? Now notice that I'm not putting the word unique here because it need not be unique. There could be several, finitely many, infinitely many different choice functions that you can define on the same collection omega, right? So the axiom of choice says, regardless of the non-empty collection of non-empty sets that you have, there always exists a choice function that you can define on that set. Now that we've defined a choice function and discussed the axiom of choice, now let's move on to Zorn's lemma and some of the things that it requires us to know in order to define and use it. So let's start off by giving a relation R on some non-empty set S. So we say that this relation R is a partial ordering on S if for any x, y, z in S, we have the following three properties. So if x is related to x, then that implies that x is an element of this relation. So this sometimes is called the reflexive property for the set S, right? So this practically says, in some sense, what partial ordering is doing is trying to define, like a less than or equal to, less than, greater than or equal to, greater than type of relation on the set S, right? So this is like your 5 is less than or equal to 5. Right? So this next property says that if x is related to y and y is related to x, that means x and y must be equal to each other. So this is what we refer to as the anti-symmetric property. So the anti-symmetric property. So that means if you think of this from, say, less than or equal to on R, if x is less than or equal to y and y is less than or equal to x, that means x and y must both be equal to each other, right? And this can somehow be related to the trichotomy property for the set of real numbers. And the last property, if x is related to y and y is related to z, then x is related to z. So if 5 is less than or equal to 6 and 6 is less than or equal to 7, that means 5 is less than or equal to 7. And you probably can guess what the name of this is. This is called the transitive property for partial orderings. And if all three of these things are satisfied, then sometimes we will say that S with that ordering R is called, some people call it a poset, or a partially ordered set. Now, a common question that I get for this definition is, why do we call it anti-symmetric? So let me just mention what symmetric means in terms of this definition. So symmetric is x is related to y if and only if y is related to x. Right? Now, this is called the symmetric property for a relation. And keep in mind, we do not want this for, say, the less than or equal to ordering on R, because 5 is not less than or equal to 6 if and only if 6 is less than or equal to 5, right? Because one of those is definitely false, right? So we definitely don't want this symmetric property there. right? That's practically why we want that anti-symmetric property, right? So 5 is less than or equal to 6, and 6 is less than or equal to 5, if and only if 6 and 5 are indeed equal to the same exact object, right? Which obviously would be a contradiction in the general sense, right? So the next thing I want to define, what's called definition of 3, is a special type of partial ordering, and it just adds one little property. So if SR is a partially ordered set with the additional property, let's call it property 4, so we have that x is related to y, or y is related to x, right? So in some sense, you can always compare one thing to each other. Sometimes people will call this the connectedness property of your set S, right? So let's take the set of real numbers, for example. If I give you the numbers 7 and 10, then either 7 is less than or equal to 10, or 10 is less than or equal to 7. One of them must be true, or at least one of them must be true, right? So that's an exclusive or, right? So if we have this fourth property, where in some sense everything is comparable, then SR is called a totally ordered set. And I guess you could create your own name for this and call it, say, a toe set. Right? Po set and toe set. Right? So toe set, totally ordered set. Right? So that is what a po set and a totally ordered set is. Right? And let's actually formally state that little comment I made, because that's actually pretty useful. So if we have a po set, what we have is the elements can be compared, but not every element, not every two elements need to be comparable. Right? So if we draw a little tree diagram here, let's assume we have, for example, A here, and let's assume we have B here. So in this notation, I'm implying that, for example, like A is less than or equal to B, and if I draw this little arrow here to some say C, then that means that B is less than or equal to C. Now if I draw a little branch off of A, for example, let's go over here and let's say D, then obviously this little arrow means that A is less than or equal to D, right? So that means if we have this particular relation R, then we have, for example, A, B, we also have B, C, and obviously if A is less than or equal to B and B is less than or equal to C, then we also have that A is less than or equal to C. We also have A, D in that particular relation, and that's all we got, right? So if somebody were to ask you, well, what about B and D? Are they related to each other? Well, there's no arrow sort of connecting these two, so BD and DB are not necessarily in this relation. Now, fun little discussions can be made when you start connecting these. For example, let's suppose I, create that little arrow between B and D. Is this a partially ordered set? Well, the answer to that would be no, right? Because here, or actually, no, I'll let you investigate that for your own. Right? So that's pretty much what a partially ordered set is, and a totally ordered set is where we can actually compare any two elements to each other. So in some sense you would have just this A, B, C, D type of thing. Some people also call this a chain. Right? So let's actually define that. So definition number 4. So a chain is a totally ordered subset of a po set, right? So in this previous example, AB is a chain, BC is a chain, ABBC is a chain, AD is a chain in that first diagram, and here AB, BC, CD, BC, ABCD, that whole entire thing is a chain, right? So now that we know what partially ordered sets are, totally ordered sets are, and also what chains are, now let us go to Zorn's lemma, right? The third main character of today's story. So Zorn's lemma. Zorn's lemma. Smiley face. All right, so what does Zorn's lemma exactly say? So suppose that SR is a poset for which every totally ordered subset has an upper bound. If this is the case, then SR has a maximal element, right? So if SR is a poset for which every totally ordered subset has an upper bound, then SR has a maximal element. So let's sort of explore Zorn's lemma for just a moment. So let's assume that we have A, B, C, obviously a poset. Also, if we look at just A, B, C, that chain, it's also, of course, a toset as well, right? So in this particular picture, C is an upper bound, right? So when we say upper bound, and let's assume that this is called X, that means that X is greater than or equal to A for all A in that set S, right? Now, it doesn't have to belong to that set. In this particular example, it does. For example, if we think, for example, for our functions, let's assume we have some horizontal asymptote. Let's assume that, this function approaches that. So this is common for like exponential functions. And if this is like y is equal to 5, then obviously if we have this line up here, which is y is equal to 6, 6 is an upper bound for this exponential function, right? 5 is also an upper bound for that particular function, even though 5 and 6 do not necessarily, at least in the finite domain, belong to that relation, right? But in this little example that we have here for this A, B, and C, we definitely have that upper bound does exist and is equal to C. And one could also say that B is an upper bound for a subset of this chain as well, because keep in mind AB is also a chain and B is an upper bound for that chain. And one could say that A is also an upper bound for itself because A is less than or equal to A for all A in that singleton set containing A only, right? So if every totally ordered subset has an upper bound, then this poset has a maximal element. A maximal element. So that means this element that is an upper bound must belong to that particular set, and it must be greater than or equal to those things, right? So let's just quickly distinguish between these two things. So upper bound versus maximal element. So upper bound, maximal element, right? So upper bound, let's call them X for both of them, right? So upper bound requires that X must be greater than or equal to A for all A and S, and maximum element also requires that X greater than A for all A and S, but A need not belong to S, and in this case, A must belong to S. So that's the distinguishing characteristic between upper bound and maximal element. Some people will also call maximal element the maximum of that set, right? So now that we have these particular things, in particular Zorn's lemma, the axiom of choice, and the well-ordering principle, now let us go ahead and prove that these three statements are indeed equivalent to each other. Before continuing onward, I just want to take a brief moment and discuss four concepts that are very closely related in terms of their names, but have very subtle differences in terms of their common definitions. And of course, I want to put out a little disclaimer that I have seen some textbooks and some professors define these in certain ways. So I'm just going to sort of present this in terms of the greatest common factor of definitions that people present these with, right? So the maximal element, the greatest element, sometimes called the maximum, the upper bound, and the least upper bound. Now, if we're dealing with like totally ordered sets, sometimes some of these terms are synonymous, and I guess that's where a lot of the confusion does come into play, because we spend a lot of our time dealing with the set of real numbers, which is obviously a totally ordered set, right? But generally speaking, a maximal element can be viewed in the following little diagram. So let's assume that we have the partially ordered set. A is related to C, and A is related to B in these particular directions. In particular, B is greater than or equal to A, and C is greater than or equal to A. Right? So we call B and C maximal elements. Right? So this is what we call a maximal element. In some sense, you can say that a maximal element is greater than or equal to, if we're using that notation, all elements within its chain. Right? So obviously BA forms a chain, CA is a chain, therefore since B is greater than or equal to A, and that's the greatest element in that chain, then that is a maximal element within that particular chain. Now obviously notice I'm using the word greatest element, but I'm using the word chain along with it. So with greatest element of a poset, then what you would have is probably a picture that looks more like this, right? So if we have this here, A is greater than or equal to B, and A is greater than or equal to C, obviously in the left-hand side, A is a maximal element for the chain BA, and A is also a maximal element for the chain AC. So you could say that the greatest element, or the maximum, is an element that is the maximal element across all chains within that poset. One could define it as so. And upper bound, again, that's where we have, for example, like some symbol like infinity, let's say, and we have, for example, A here, and we have B here, but infinity typically is not defined as a number, more so a concept, but here we have A is less than infinity and B is less than infinity, but in this case infinity does not necessarily belong to our poset, so technically these are dotted lines, not really arrows, because you can only approach it but never touch it. So in that case, infinity would be an upper bound for that particular set. And then we have the least upper bound, which can be viewed very closely to upper bound. So to sort of distinguish between these two, let's go back to our little horizontal asymptote question, right? So let's assume we have this particular curve, where horizontal asymptote is, say, again, let's say y is equal to 7. And let's assume that this function is monotonically increasing on the set, on its entire domain. So obviously, if we have, for example, 8 is an upper bound for this particular set. We also have that 10 is an upper bound for this particular set as well. So since they do have upper bounds on the entire domain, sometimes we say that this function or relation is bounded. But if it has an upper bound, does it necessarily have a least upper bound? We'll revisit that theorem a little bit later, because do notice that 7 also is a upper bound as well, but it is the least upper bound. Right? So how would you prove that 7 is the least upper bound for this set? Well, you would assume that there's some another upper bound, say 7 minus epsilon, that is a upper bound, and show that, you know, this function eventually reaches the y value of 7 minus epsilon for some given x in the particular domain, and that would contradict that that is indeed a upper bound, because the function goes above it eventually, and that would generally show that the least upper bound is 7. right? So if you choose, for example, 8, and you say, oh, well, is 8 the least upper bound for this particular relation? All you have to do is say, okay, 8 minus 7 is 8, or is 8 minus epsilon a part of the range of that particular element? And if you can show that that is not the case, then in some sense you do have evidence to believe that it might be least upper bound. But again, there's several different theorems that sort of help us prove least upper bound. And some people will even use LUB for least upper bound for a particular set S. And some people will even use SUP of S, which is short for supremum. Right? So there's another word to add to our list. So supremum. Right? So supremum and least upper bound are sometimes taken to be synonymous. I wouldn't say sometimes, I would say most of the time. Right? But there's these 5 different concepts that are loosely related, but not necessarily equal to each other. And we also do have their counterparts, because we also have a minimal element, and then we have a minimum, or a least element, and then we have a lower bound, and then we have a greatest lower bound. And then we also have an infimum, right? And greatest lower bound sometimes used GLB of S, and an infimum sometimes uses the notation I and F, and these practically fall in an analogous way to their opposite counterparts. But I just wanted to mention this here, just in case you are curious about their notation, because we're definitely going to be focusing on these a little bit later, but now's a good time at least to be familiarized with their definitions. Now let's move on to our main part of the story. So up to this point, we have the well-ordering principle, Zorn's lemma, and the axiom of choice. So our guiding question for this discussion was, which one can, or which one should, we choose as our unifying and foundational axiom? Well, one person may be like, well, axiom of choice has the word axiom in it, so maybe we should choose axiom of choice as our baseline axiom and show that axiom of choice implies well-ordering principle and Zorn's lemma, and in some sense that would be perfectly fine. But the actual question is, which one can we choose as our axiom? The correct answer is any. And that's pretty nice, right? So now let us state the theorem that we need to prove in order to show that we can actually choose any. So this theorem says the following: the well-ordering principle, Zorn's lemma, and the axiom of choice are all equivalent to one another. That is, if you assume one, you can prove the other two, regardless of the one that you have proven. So let's start off by proving this. So all we have to do is in some sense create a cycle. So we can show that the well-ordering principle implies Zorn's lemma implies axiom of choice, and for example prove that axiom of choice proves well-ordering principle, and that will complete that cycle of proof, right? So the first theorem that I want to prove is the following. In particular, well-ordering principle implies axiom of choice. I think this is the easier one to prove amongst any of the permutations. All right, so let's see if we can prove this. So let's suppose, so we're assuming the well-ordering principle is true. So suppose that S is a non-empty set, and R is a total ordering on S. Does there always exist a choice function on this particular set S, right? So we're assuming that S is a non-empty set and R is total ordering on S, and we can assume that there exists a total ordering because that's what the well-ordering principle states, generally speaking. So does there always exist a choice function on X, because that's what the axiom of choice states as its conclusion? Well, let's see if it does. So if we're assuming that we have a non-empty set and R total ordering on that set, then the well-ordering principle guarantees the existence of what? So remember, the well-ordering principle, if you don't remember, states that every non-empty subset has a least element. So if that is the case, some people will also call it a minimal element as well. So it guarantees the existence of a minimal. In some sense, minimal and least are synonymous since we're dealing with the total ordering. So a minimal or least element of S. So if it guarantees the existence of a minimal element, then how are we going to define our choice function? So what we have to do is define f of this to be equal to the minimum of this set S. Right? So since we're guaranteed an existence of a minimum, this function always exists. Right? So that means a choice function always exists. Right? And that completes the proof. Now notice that, there could be other ways I could define this, right? Because we're not claiming that a unique choice function exists. Axiom of choice says that there exists a choice function, not necessarily unique, remember, right? And since we're guaranteed a minimal element for this set, we can always define our choice function. Give me a set, I'll return the minimum of that set, which always exists by assumption, right? So that's the first thing. So we have that well-ordering principle implies the axiom of choice. Now let's move on to the second. Now that we have that the well-ordering principle implies the axiom of choice, now let us see if we can get the axiom of choice to imply Zorn's lemma, and then the only thing that would be remaining is to show that the Zorn's lemma implies the well-ordering principle, and then we have that all three of these statements are equivalent to each other. So axiom of choice implies Zorn's lemma, right? So let's start off our proof. So what we're going to do is we're going to let S be a non-empty poset with every chain having an upper bound. Right? And you're like, okay, well, where is this assumption coming from? So this assumption is coming from Zorn's lemma, right? So this is the assumption of Zorn's lemma, right? And keep in mind that this, at least directly, does not necessarily imply that there exists a maximal element, right? The existence of a maximal element for that poset, that's what Zorn limit concludes, right? So this right here, that's our goal, right? So our assumption at least does not directly imply that, right? But it's the same premise as Zorn's lemma, not the conclusion, right? So we're going to be letting S be a non-empty, partially ordered set with every chain having an upper bound. So let's see if we can get Zorn's lemma out of this. So if we're going to see if there exists a maximal element in this set, let's actually go ahead and assume that such a maximal element does not exist. Let's see if we can do a proof by contradiction. So let's assume that a maximal element does not exist. All right? Let's hope and pray that we can find that contradiction. Right? Because if we assume that maximal element does not exist, then this will imply that Zorn's lemma is false. Right? So what we're going to do is we're going to choose an X in S. So again, what allows us to be able to choose an element in this set? Obviously that's coming from the axiom of choice. Right? So what can we say? So we're going to be assuming that a maximal element does not exist, and we're choosing a particular element in this set, which we're always allowed to do under the axiom of choice. What can you tell me about this element that I'm choosing? Well, since X is not maximal, then that means there must exist some element, let's call it y1, in S, such that x is related to y1. There has to be an upper bound for that element under the assumptions that we have. Now again, y1 is not the maximal element because it doesn't exist, right? But keep in mind, this notation is equivalent to us saying that x is less than or equal to, say, y1. It's just a different notation, right? So, continuing in this fashion, since y1 also is not maximal, that means there exists another element, y2 and s, such that y1 is related to y2. Fair? So what we're going to do is we're going to continue this on and on and on, right? So if we continue this, continuing this gives us a chain that looks like the following, right? Because we chose our x, and that's less than or equal to y1, that's less than or equal to y2, and that's less than or equal to y3, and so on. Now, it's possible that we chose an element that's not the minimal element, but we're not focused on minimal elements with this, right? Zorn element. Zorn's lemma is focused on the maximal element, right? So notice that this continues on forever. This continues on forever. This is important. This is very, very important. Right? So let's see if we can build our contradictions. So, case 1. So if S is finite, right? And you probably were thinking, right? Is it possible that, we choose an X and it's a singleton set, and therefore we cannot choose a Y1 because, Y1 would then be equal to X, right? So if S is finite, this chain is an infinite sequence, right? And that would lead us to a contradiction, because if it's a finite set, this cannot continue on forever. Fair? So there would be our contradiction, and then we would be done with the proof if that was the particular case, right? So now let's consider the case where S is infinite. So if that is the case where infinite, then what we're going to do is we're going to define the cardinality of this set to be equal to omega. Obviously, omega is not finite. It's like infinity, like the size of the natural numbers, or the sign of the rationals, or the size of the reals, or the size of the power set of the reals, or something like that. And let's also assume, that without loss of generality, we're not really going to lose much of this. Let's assume that omega is the upper bounds of, let's also call y omega, is the upper bound of this chain, x, y1, y2, all the way up to y omega. Obviously, y omega is greater than or equal to all those, so it's definitely an upper bound, right? So keep in mind, that would have to be the last element in that sequence, right? So if that is the case, then what do we have? So still, this infinite chain does not have a maximal element. And since it does not have a maximal element, that means there must exist a y omega plus 1, such that y omega is related to y omega plus 1. Right? So, which means that this relation has a cardinality that is bigger than S, right? So that means eventually we will have more elements than S contains, right? And that obviously will lead to another contradiction, right? And that completes, both sides of this story, right? So since this little sequence can always exist, that means a maximal element must exist. If every totally ordered subset of a poset has an upper bound, right? which is Zorn's lemma. Right? And the only thing we assumed was the ability to choose an element, implying that there exists another element that is above it. Right? So that completes the proof of that implication. Fair? So at this point, what exactly do we have? So we have that the well-ordering principle implied the axiom of choice, and we have that the axiom of choice implies Zorn's lemma. Now keep in mind, if these are equivalent, you could also show that axiom of choice implies well-ordering principle, and you could also show that Zorn's lemma implies axiom of choice, and that actually would conclude your proof of equivalence between these three statements. Or you could show that Zorn's lemma implies well-ordering principle if you follow our sequence, and that would be perfectly fine, right? And equivalently, if these are equivalent, that means well-ordering principle can be used to prove Zorn's lemma, right? So the third theorem would be that Zorn's lemma implies the well-ordering principle, and I'll leave that for you just for fun. I think that might be the easier of the other directions that you could prove, right? Because if you want to go the other way, you would have to show that Zorn's lemma implies axiom of choice, and axiom of choice would imply well-ordering principle, or you could just show Zorn's lemma implies well-ordering principle, and then you'd be done with that sequence, right? So if that is the case, that means these three statements are equivalent, right? Now, I do want to do or mention just something very, very slightly, especially if you've taken linear algebra, right? So if you know anything about linear algebra, you might know a lot of things about vector spaces. So keep in mind, if you have the axiom of choice, then this is true, actually, if and only if every vector space has a basis, right? That's actually pretty nice. Now, I'm not going to go ahead and prove that these two statements are equivalent, because in some sense they're completely different worlds, right? But keep in mind, our focus is real analysis, but you could use the axiom of choice to prove other theorems that are useful in linear algebra, such as this amazing theorem about how every vector space having a basis. But in the realm of real analysis, us proving Zorn's lemma and the well-ordering principle are going to give us a lot more machinery to prove things that are of use to us, at least in this discussion. For example, we've already proven that the well-ordering principle proves mathematical induction, which is very, very useful in sequences of natural numbers and also the set of integers as well, right? But that concludes the proof, or in some sense the proof, since I'm leaving one thing for you, of the equivalence between Zorn's lemma, axiom of choice, and the well-ordering principle. So I hope you enjoyed this video, and I'll see you in the next episode of Real Analysis. Take care.